Hello everyone! In this video, we'll continue to examine topic 5.2, the heating effect of electric currents, and in particular, we will finish up Kirchoff's second law. All right, so why did we go through this? Well, partly it was to deal with like this kind of situation or this kind of situation, but actually we probably didn't need this sort of Kirchoff's second law analysis tool to deal with this. I probably could have just waved my hands and said, doesn't it seem straightforward that one of the batteries is going to subtract the EMF of the other? Well, as it turns out, there's a deeper reason, which is that Kirchoff's second law allows us to analyze circuits that look like this, which otherwise we do not have the ability to analyze. Okay, so this kind of a circuit where, notice, I have more than one battery, the batteries sort of non-obviously are driving current in different directions at different points in the circuit. Notice we're not going to be able to analyze this with only resistors and reduce it in the same kind of way. So this kind of circuit, which is pretty straightforward to build and can be solved, cannot be solved without something like Kirchoff's second law, right? Which is why we're spending some time dealing with it. So again, for this example, you're welcome to try it out on your own, right? Try applying Kirchoff's law to the various loops within the circuit. So I would encourage you to sort of write this out, pause the video at this point, and draw out this circuit, and then label the three possible loops. 1, 2, all the way around, and then 3. Within this little branch. And remember that sort of procedurally, you first guess and label the current directions, okay? If you're wrong, that current will come out negative. Then apply Kirchoff's laws to each loop. Then solve, okay? And I'm gonna give you some values here, but solve for the case that all the resistors are 2 ohms and that the two sources of EMF are 6 volts. By solving the system of equations that you end up with. So we're going to see what this means in a second. So I'd encourage you to pause and see if you can write down the equations that apply to the 3 loops right now. All right, so we're going to do it loop by loop here. I'm going to write the equations first, and then we're going to see how to solve them using our values. Okay, so I will say that for the IB, it is most important that you be able to write the equations in abstract variables. So actually solving the equations out, which is something the book will ask you to do, and I might ask you to do, is probably not going to be something to expect on the exam, in part because mostly it's math, and in part because it takes a long time. So they just don't bother with it. Okay, so loop 1, all right? We're going to keep track of this thing first. All right, if we draw our loop, we're going to go up EMF 1, right? I1 is drawn to go through R1, so we go up EMF 1, down I1 R1. I2 has been guessed to go this way, so down I2 R3, and then down I1 R2, because our loop direction is in the same direction as the current in R2. So if we take a look at that equation, it's through EMF 1, down I1 R1, down I2 R2, down I1 R2. Okay, so our first loop is fairly straightforward. Okay, all the currents and the EMF in that loop sort of behave normally. All right, now let's take a look at our second loop. That's the one that goes all the way around. All right, well, similarly, okay, if we start out, we go up EMF 1, that's good. And then down I1 R1, okay, so we're going to hit this resistor next, just like before. But then we go this way, all right, and notice we are crossing, in this loop, we're crossing the potential gain of this battery, which is wired up just fine, it's not even a miswiring, in the wrong potential difference direction. So that is a potential drop, and therefore that is negative EMF 2, so dropping through that potential difference. Then we're going to cross this resistor here. Notice the current is going in the opposite direction. So we are also going to rise in potential difference through this resistor. So now we're minus EMF2 plus I3R4. Okay, and then we have one more term. Don't forget, we're going to hit this resistor as well, but finally our labeled current is in the same direction as our loop direction. And so that's minus I1R2. Great. Okay, so those are two equations. I'm going to note at this point that with these two equations plus Kirchoff's first law, which we'll apply in a second here, you can solve everything you need. So you don't have to do the third loop, but for the sake of completeness, all right, remember this third loop is this way. All right, so we can start anywhere we want. Usually I start at the battery. So if our third loop is in this direction, then we're going to go up EMF2, okay, and then cross I2 R3, this particular resistor, in the same direction as the current, so minus I2 R3, and then again minus I3 R4 equals 0. So this loop, that yellow loop, is also pretty straightforward. Notice that I'm about to solve this set of equations for these values, but you only need 2 of these 3. You then want to apply Kirchoff's first law at one of these junctions, which is much more straightforward, and you get that I1 plus I3 equals I2 as labeled here, or here. So in this, if we look at this junction, I2 is equal to I1 plus I3, okay? And that gives us this. So now that we have these equations, and this is really what you need to be able to do for the IB, they will ask you for this set of equations, right? Kirchoff's second law is applied to sort of different loops in the circuit. Then you plug in our values. So we're told to solve for the case that R1 is R2 is R3 is R4 is 2 ohms, and EMF1 equals EMF2 equals 6 volts. By the way, you'll notice that these values are chosen to make the equation a little more, or the set of equations a little simpler to solve. This is an expected math skill for this class, but it's not our point of emphasis. And if we were using arbitrary resistances and arbitrary EMFs here, so not ones that are identical, this gets really hard. I mean, hard is the wrong word. It just gets like lots of algebra. So we'll look at this particular example. If I plug in those values into my first equation, this should actually say K2 here. So I'm going to plug my values into this equation. Then I get 6 volts minus I1, which we don't know, times 2 ohms, minus I2 times 2, minus I1 times 2 equals 0. Okay, and if I plug it into my second, this is what I get. 6 minus I1, 2, minus 6, plus I3, 2, minus I1 times 2 equals 0. That gives us 2 equations here with 3 unknowns, but then what I can do is plug in Kirchoff's first law. So I substitute in for I1 here. I1 is equal to I2 minus I3, and I then can distribute and solve out algebraically for just 2 equations with 2 unknowns. Okay, and that's what these steps are. So these are just algebra steps, except from here to here, we substituted in using Kirchoff's first law. Same for this step as well. Then we have equations A and B. We solve those linear equations here by taking 2 times equation A minus 3 times equation B. That gives us this. That gives us a value for I3 of 1.2 amps, and then you plug back in to either of the equations or any of the equations you need to get I2 and then I1, okay? So that's how you would use this equation to solve for the currents in a circuit like this. What you will be expected to do in the IB is to be able to take a complex circuit like this and analyze it using that system of equations and to write down the system of equations. That's the most important part. So that's the step you should practice. Here's an example of sort of applying Kirchhoff's second law, particularly number 2, to this kind of a circuit.